When sizing the neutral wire for an equipment subpanel serving a combination load, such as a pump, heater, and control panel, several factors must be considered according to the National Electrical Code. Firstly, we must refer to NEC Table 310.15 B6, although it's essential to consult the latest edition of the NEC for the most accurate and up-to-date information, as code requirements can change between editions. The neutral wire should be sized based on the higher of two calculations. 1. The neutral current calculated using the load current multiplied by the neutral factor, which in many cases is 0.7. 2. The largest ungrounded phase conductor size. To illustrate this, let's assume the load is 90 amps and the ungrounded conductors are #2 copper. The neutral current is calculated as 90 amps multiplied by 0.7, which equals 63 amps. We then compare this to the size of the #2 copper conductors. Since #2 copper is larger than what is required for 63 amps, the neutral wire must also be sized at #2 copper. This ensures it can safely carry the maximum potential neutral current. Now let's discuss ground wire sizing for an equipment panel. The ground wire functions as the equipment grounding conductor, or EGC. NEC Table 250.122 provides guidelines for sizing the EGC based on the rating of the overcurrent protective device protecting the circuit. For a panel with a total load of 100 amps or less, the EGC can be sized according to this table. In this case, for a 100 amp feed, a copper wire sized as #8 American wire gauge is sufficient. Therefore, the ground wire for this panel can be #8 copper. In conclusion, for a 100 amp equipment panel serving a combination load of 90 amps, using #2 copper conductors for the ungrounded conductors, the neutral wire must be sized as #2 copper, and the ground wire can be sized as #8 copper. It is crucial to remember that these calculations are based on the information provided and the specific requirements of the NEC. Always consult the latest edition of the NEC and seek the advice of a qualified electrical professional for any electrical work to ensure compliance and safety. Let's delve deeper into the NEC requirements for neutral and grounding conductors to provide a more comprehensive understanding. The neutral conductor carries the unbalanced current from a 3-wire or 4-wire circuit back to the source. In a balanced 3-phase system, the neutral current is ideally zero, but in reality, loads are rarely perfectly balanced, leading to some current flow on the neutral. The NEC mandates specific sizing requirements for neutral conductors to ensure they can safely handle the anticipated unbalanced load current. Several factors influence the neutral conductor size, including the type of load, the presence of nonlinear loads, and the applicable directing factors. For predominantly resistive loads, the neutral current is typically lower than the phase current, allowing for a smaller neutral conductor. However, when nonlinear loads, such as electronic equipment and LED lighting, are present, they generate harmonic currents that can significantly increase the neutral current. In these cases, the neutral conductor must be sized to accommodate the harmonic currents to prevent overheating and potential fire hazards. The NEC provides guidelines for calculating the neutral load based on the type of load served. For example, Section 220.61 allows for demand factor to be applied to the neutral load calculation for household ranges and cooking appliances, recognizing that not all appliances will operate at their maximum rated loads simultaneously. However, this demand factor may not be applicable in other situations, such as commercial kitchens where multiple cooking appliances may be used concurrently. In addition to load calculations, directing factors may also affect the neutral conductor size. When multiple conductors are installed in a raceway or cable, their ampacity must be derated according to NEC Table 310.15 B3, to account for the increased heat generated by the conductors. This derating factor can impact the required size of the neutral conductor, particularly in installations with a large number of current-carrying conductors. Let's now turn our attention to equipment grounding conductors, or EGC. The primary purpose of the EGC is to provide a low-impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The EGC also helps to minimize the voltage potential between metal equipment enclosures and ground, reducing the risk of electric shock. The NEC specifies the minimum size of the EGC based on the rating of the overcurrent protective device protecting the circuit, as shown in Table 250.122. For example, a 20 amp circuit requires a minimum #12 American wire gauge copper EGC, while a 100 amp circuit requires a minimum #8 American wire gauge copper EGC. The EGC can be either a wire or a metal raceway, such as electrical metallic tubing or rigid metal conduit. When using a metal raceway as the EGC, it must be properly installed with fittings listed for grounding to ensure a continuous and reliable ground path. In addition to sizing requirements, the NEC also addresses the installation of EGC. Section 250.130 outlines the requirements for grounding equipment connected by cord and plug, while Section 250.134 covers the grounding of fixed equipment. These sections specify the methods for connecting the EGC to the equipment enclosure and the grounding electrode system. The grounding electrode system provides a connection to earth, ensuring that the electrical system is at a relatively stable voltage potential with respect to ground. The NEC specifies the types of grounding electrodes that are permitted, including metal water pipes, ground rods, and concrete encased electrodes. The grounding electrode system must be properly installed and maintained to provide an effective ground path for fault current. In summary, the proper sizing and installation of neutral and grounding conductors are critical for ensuring the safety and reliability of electrical systems. The NEC provides detailed guidelines for determining the appropriate conductor sizes and installation methods based on the specific characteristics of the electrical system. Always consult the latest edition of the NEC and seek the advice of a qualified electrical professional for any electrical work to ensure compliance and safety. Consider a scenario where you're dealing with a 208-volt three-phase system feeding a subpanel. The main breaker protecting the subpanel feed is rated at 60 amps. The subpanel serves a mix of lighting, receptacles, and a small motor. Firstly, determine the minimum size of the equipment grounding conductor. Referring to NEC Table 250.122, for a 60 amp overcurrent device, the minimum size copper equipment grounding conductor is #10 American wire gauge. This conductor must be run with the circuit conductors to the subpanel and properly connected to the subpanel's grounding bar and the metal enclosure of the subpanel. Secondly, calculate the neutral load. To do this accurately, you need to analyze the loads connected to the subpanel. Assume the lighting load is 10 amps, the receptacle load is 20 amps, and the motor load is 15 amps. Since this is a three-phase system, the neutral current for balanced three-phase loads is ideally 0. However, single-phase loads connected line to neutral will contribute to neutral current. Assume half of the receptacle load, or 10 amps, is connected line to neutral on one phase. The lighting load is also connected line to neutral. Therefore, the total neutral current is 10 amps from the receptacles plus 10 amps from the lighting, totaling 20 amps. Referring to NEC Table 310.16, a #12 American wire gauge copper conductor is typically rated for 20 amps at 75 degrees Celsius. However, several factors could require a larger neutral conductor. For instance, if there are significant nonlinear loads present that generate harmonic currents, the neutral current could be substantially higher. In this case, a detailed harmonic analysis would be necessary to determine the actual neutral current. Additionally, if the conductors are run in a conduit with more than 3 current-carrying conductors, ampacity-directing factors would apply, potentially requiring a larger conductor. Assuming no significant harmonic currents or directing factors, a #12 American wire gauge copper conductor would be the minimum acceptable size for the neutral. However, it's generally good practice to use the same size conductor as the phase conductors, which would likely be #6 American wire gauge copper for a 60 amp breaker to provide extra capacity and ensure consistency throughout the installation. Let's consider another example. Imagine a 480-volt three-phase system feeding a piece of industrial equipment. The equipment has a total load of 50 amps and is protected by a 50 amp circuit breaker. The equipment includes motors, heaters, and electronic controls. Firstly, determine the minimum size of the equipment grounding conductor. Referring to NEC Table 250.122 for a 50 amp overcurrent device, the minimum size copper equipment grounding conductor is #10 American wire gauge. This conductor must be connected to the equipment's metal enclosure and run back to the source of the power supply. Secondly, determine if a neutral conductor is required. In a 480-volt three-phase system, if the loads are strictly line-to-line, a neutral conductor is not required. However, if any of the loads are connected line to neutral, such as 277-volt lighting or control circuits, a neutral conductor would be necessary. Assume this equipment includes a 277-volt control circuit with a load of 5 amps. The neutral conductor would need to be sized to carry this 5 amp load. Referring to NEC Table 310.16, a #14 American wire gauge copper conductor is typically rated for 15 amps at 75 degrees Celsius, which would be sufficient for this 5 amp load. However, as with the previous example, factors such as harmonic currents or dirting could necessitate a larger conductor. In this case, it would be prudent to use at least a #12 American wire gauge copper conductor for the neutral, providing some extra capacity and ensuring mechanical strength. Remember to always consult the latest edition of the NEC and consult with a qualified electrical professional to ensure the electrical system is safe, reliable, and compliant with all applicable codes and standards. It's also important to consider voltage drop in conductor sizing. While the NEC provides minimum conductor sizes for ampacity, it's equally important to calculate voltage drop to ensure that the equipment operates correctly and efficiently. Excessive voltage drop can cause motors to overheat, lights to dim, and electronic equipment to malfunction. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor length, the load current, the conductor size, and the conductor material. Online voltage drop calculators and software tools can simplify this calculation. If the calculated voltage drop exceeds the recommended limits, you may need to increase the conductor size to reduce the voltage drop. Furthermore, consider the environmental conditions in which the conductors will be installed. High ambient temperatures can reduce the ampacity of conductors, requiring larger conductor sizes. The NEC provides ampacity correction factors for various ambient temperatures. Conductors installed in direct sunlight may also require additional protection to prevent degradation of the insulation. Additionally, corrosive environments can damage conductors in raceways. In such environments, it's important to use corrosion-resistant materials such as stainless steel or PVC-coated conduit. Regular inspections and maintenance are essential for ensuring the long-term reliability of electrical systems. Inspect conductors for signs of damage, such as cracks, abrasions, or corrosion. Check connections for tightness and proper insulation. Test grounding systems for continuity and resistance. Address any issues promptly to prevent potential hazards. Proper documentation is also crucial for electrical systems. Maintain accurate records of conductor sizes, circuit layouts, and grounding system configurations. This information is invaluable for troubleshooting and future modifications to the electrical system. In conclusion, designing and installing electrical systems requires a thorough understanding of the NEC, electrical theory, and best practices. Paying attention to detail and prioritizing safety are paramount. By following these guidelines, you can ensure that electrical systems are safe, reliable, and compliant with all applicable codes and standards. Remember that electrical work can be dangerous, and it should only be performed by qualified individuals. If you are not comfortable working with electricity, hire a licensed electrician to do the job.